Am I audible to everyone? Okay, 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 great. So we share. Just yeah.
Public.
Yes. Let me know if there is any audibility issue. Uh, because I'm using an earphone today. Just let me know. So
Yeah.
today, yeah. So today, where we left in the last classes, basically we have seen a certain kind of a mathematical representation of different quantum states, how it behaves, and how the different kind of a row vector represents a bra notation and a column vector represents a ket notation, and
Yes,
how
Ariana.
for
Voice.
different multi-qubit systems you can represent quantum states, and what are their different interpretations. We have also seen that how the probabilities of different quantum states you can understand from the like wave function in a superposed form, and what is the meaning and interpretation of probabilistic amplitude and the probability corresponding, and how they are different, how they are related, all those things we have seen. So
Break. Ma'am, there is a slight disturbance in the voice, I think.
let now is it okay? Is it better now?
Yeah, slightly only. Yeah, yeah. You start. Go ahead. Let's see.
Okay, okay, yes.
Yeah, yeah, yeah.
I have certain issue with my running nose and all. I'm having some fever, so maybe there is a little somewhere I might be not be able to speak very loudly. Just let me know. Then we will again just repeat the concepts. No issue. Yes, Swati Nigam, no voice. Is there no voice? It's fine. Thank you. Thank you, everyone. Thank you, everyone. So that was the concept. So today we will be discussing about a few of the mathematical concepts which we need mainly from the linear algebra side. There are certain things as well which we will be covering while we will be doing the plot sphere representation. Because yesterday only we seen a certain matrix form. So today we will be discussing a bit of those things mathematically from the vector space and matrix representation. Followed by, we will see some of the quantum bits or qubit concept, along with, if today time permits, we will see a certain form of quantum gates, which are very basic quantum gates, but at least we will be having an understanding that how different quantum gates can work as a quantum operator, which is nothing but the matrix form of the quantum operator. We can have that idea. So with that kind of an agenda, let me start today. So, yes, I hope the agenda is clear to everyone. So first we will be discussing about, and I will be having a very slow pace today. If you are having any doubts in between, just put it on chat. If it is very relevant to the topic that I'm discussing, I will be more than happy enough to discuss it in that very instance. Otherwise, I will just put a pause and try to resolve it at the very end of our session. That will be the entire plan. So, firstly, it's a big thing to discuss about the vector space that we have, which is kind of a playground for quantum states during the time evolution. So, the foundation of quantum computation is nothing but a collection of vector spaces. You can think it of. So, imagine you are in a vast playground where you can move in any direction. The rules of the playground determine how far you can go, how you can combine your different movements, and how different movements interact with each other with courses of time. So this playground represents a vector space. It is kind of a mathematical stage on which a quantum mechanics and quantum computing can take place. So in classical physics, your objects can exist at definite locations, but in quantum mechanics, the state of a system is like a direction in this playground. That is, it is completely a kind of a vector. You know that a vector has a certain magnitude as well as a direction. So just like that. So it is not just a fixed point which has a certain sort of scalar magnitude. So this means Your quantum states can be added together or scaled just like the moves in a game. Whatever you want to, you can actually do it. And why does it matter? Because in quantum computing, every possible state of a qubit or quantum bit is a direction in its abstract playground. Abstract means something that you are unable to predict beforehand, but it's just happening quantumly. So the ability to move freely in the space enables quantum superposition and entanglement, which are the two very basic ingredients or key ingredients of quantum advantage or quantum supremacy. Okay, now just two things. Quantum supremacy means where I can see or we can actually visualize certain sort of an exponential speed up than our classical computation, where it's like a very kind of a better approach. You can think it of in this way. Quantum advantage is where we at least get a better solution than the classical counterpart that we have right now. Okay, so just remember between these 2 points, quantum supremacy is something where it's definitely a better solution in terms of a speed up with respect to its classical counterpart. Whereas in quantum advantage, we mean that at least using some quantum hardware or logic or algorithm, we can demonstrate a certain sort of better solution with respect to the classical counterpart. Okay, so they are really different. So maybe some by some linearity you can show the difference that it is better, or some quadratically you can show, but it's definitely not a very exponential speed up. So there are different applications where we can see diversely two different kind of things, like one maybe for quantum supremacy and one maybe for a quantum advantage. Okay, now again, because there are a lot of mathematics, so I used these kind of handwritten slides. So I'll be explaining these things, keeping in mind that we need both the things together. Okay, that is a very, very theoretical explanation as well as a bit of mathematical understanding, so that we have a full 360-degree understanding of both the things. So a vector space is nothing but a collection of objects or vectors that can be added together or multiplied by some scalars while satisfying a certain axioms. And this fundamental concept in linear algebra forms a very backbone of quantum mechanics as well as a computing, where quantum states exist in complex vector spaces. There are definite criteria that quantum states fulfill. We will actually look into it in subsequent classes and maybe today also in later half. So definition is a vector space V over a field F, where usually you can think it of a real vector space or a complex vector space. The field is nothing but a real set of numbers, or a set of real numbers, or a set of complex numbers. So a vector space is nothing but a set of vectors equipped with two basic properties. One is a vector addition, that is u plus v, where u and v both belongs to the some element of the vector space. So u plus v should also be in v. And scalar multiplication is if you add the one of the elements, say u, with a scalar coefficient alpha. So both the things multiplied product will also be in vector space. And these must satisfy a few properties, like it should be commutative, that is u plus v should be equals to v plus u. It should be associative, that is u plus v plus w should be equals to u plus v plus w within bracket. Third is a zero vector existence, where you have to get a number which belong to the vector space, and if you add from an addition between that number and basically any one of the elements of your existing vector space, that should yield the same vector space number that you have. For example, very easily, say u is the number that belongs to the vector space. So mathematically, 0 belongs to v, such that this symbol is a such that notation such that u plus 0 is also u. And that again belongs to the vector space. So this is a zero vector existence theory. Okay, and the fourth one is existence of an additive inverse. So basically, we all know it. Say, for example, for a real number, if we have 5 and we should be having some minus 5, so that 5 plus minus 5 should be equals to 0. That is the additive inverse. Inverse means it's just exactly the opposite to the element what you have, and additive means the operation should be addition. So that is the additive inverse theory. So in order to be a successful vector space, your vector space should satisfy these properties, right? And these are very important. These are all the fundamentals. So it's just like you have to at least be a vector space in order to proceed for the next one. Then that also needs to be satisfied in order to make it to the next level likewise. So it's a very fundamental criteria that you have to keep in mind. Now, examples of valid vector space. Say, for example, I have a set Rn where R is the set of real numbers in an n-dimensional Euclidean space. And say, for example, R3 we have, which is a three-dimensional real space. Real space means a three-dimensional vector space with a set of real numbers. R may be represented by a V, which is a column vector with X, Y, Z. That kind of a column vector, you can see it, where X, Y, Z all individually belongs to R. So this satisfies all the vector space axioms. And example 2 is, say for example, I have a space with a complex vector states which are in quantum, that is in a complex space with two-dimensional vectors. So a quantum bit or a qubit with represented through the wave function phi or psi can be represented as alpha k0 plus beta k1. So these are the things that you can do. Just for a quick example, that what are the scenarios where you can actually, through the examples, can determine that whether it's a valid vector space or not. Say, for example, we have a question like which of the following is a not a vector space. First is the set of all polynomials with the degree less than equals to 2, set of all three-dimensional vectors with a vector addition defined as a component-wise addition. C is set of all real numbers with multiplication as the operation. And fourth is set of all continuous functions on R with point-wise addition. Let us take each and every options and just go to a little depth of it. So option 1 is set of all polynomials of degree less than equals to 2. And it should satisfy two things. One is the addition criteria and second one is the scalar multiplication criteria. So let V be a set of all polynomials of degree less than equals to 2. Say P of X is a polynomial with a like function or a parameter X, where P of X is equals to a polynomial of degree 2, which is x squared plus bx plus c, where a, b, c are the coefficients, all belonging to set of real numbers R. Now we have to check the vector space axioms, where the first criteria is whether it's closed under addition operation or not. So for that, let us choose two polynomials, p1x and p2x, which are two polynomials. Then p1 plus p2x should be a1x squared plus b1x plus c1 plus a2x squared plus b2x plus c2. Just taking common and all those things with a bit of like alteration, you can check that it's basically a1 plus a2 whole bracket x square plus b1 plus b2 within a bracket times x plus c1 plus c2, where a1 plus a2 is again a constant, b1 plus b2 is another constant, and c1 plus c2 is another constant. But even after that, if you replace a1 plus a2 with certain thing, maybe say p1 plus p2x plus p3, then also it's a polynomial of degree less than equals to 2. So a polynomial of degree less than equal to 2 definitely satisfies the addition closure property. The second one is a closure under scalar multiplication, where if alpha is a scalar, then alpha times px is equals to basically alpha times the value of the px, which is nothing but x squared plus bx plus c. So if you just take a few common and all those things, so alpha is another scalar, maybe 3, 4, 5, anything. So that times the coefficient of x squared, that is alpha into a, x squared plus alpha into beta x plus alpha into c. This will also like behave as a polynomial of degree less than equal to 2. So definitely you can say that set of all polynomials of degree less than equal to 2, satisfies the criteria of a vector space, which says that you have to follow all the additive closure properties, where definitely it has to be like commutative, associative, and like zero element should exist and additive inverse should exist. Also, it should follow the scalar multiplication property, right? So your A is definitely a vector space. So maybe we have to go for the option number B, right? If you're having any issue with the audio and all everything, let me know. So today I know that we have to bit of like be a mix up strategy. So that is why I have not put all the mathematics here for this class, and also not exactly the theoretical parts for this class. It is a blend today. Tomorrow also it will be a bit of a blend kind of a thing, so that we have a like mixed understanding. We don't get bored, because of quantum physics only, if I just follow that logic, that might seem very bored for many of you. So that is why I have picked up, I will picked up a mixed up strategy. I hope it will be fine at the end of the very class. Let us see how it proceeds. So option B, what was option B? It was a set of all three-dimensional vectors with vector addition. Thank you. Okay, what's your name? Kyle. Okay, I'm calling Kyle. So set of all three-dimensional vectors with vector addition defined as a component by as addition. So what do we mean by this? Say for example, U is a three-dimensional vector which have three dimensions x, y, y1 and x1, y1 and z1. And V is another vector with the three-dimensional parameters like x2, y2 and z2. Say for example. Now U plus V, Sumanta, please just try to rejoin. I think that's when your problem will get resolved. I don't think it's the same problem for all the other participants. Just try to rejoin. So audio is okay. Thank you. So first of all, it should be the closure under addition. So U plus V should be equals to the individually addition, which is x1 plus x2, y1 plus y2, and z1 plus z2. You can check anywhere. It will definitely be associative and commutative as well, because we are doing only with respect to the addition thing. Third one is a zero vector existence. You can check if you have a zero vector, say for example 0, 0, 0, does it really exist? Let us say prove it. So say for example you have an U which is x1, y1, z1. Forget about V. Say for example your V is a zero vector itself, which is 0, 0, 0. If I say that U plus V is nothing but x1 plus 0, comma x y1 plus 0, comma z1 plus 0, which is x1, y1 and z1. So ultimately what you are getting that U plus 0 is equals to U, right? Because x1 plus 0 is x1, y1 plus 0 is y1, and z2 plus 0 is z2. So in that way, you can verify that the zero vector 0, 0, 0 also exists for this kind of a scenario. Okay, where out of the two vectors, one you have to assume forcibly as a 0, 0, 0. That was the logic. And fourth one is whether the additive inverses exist or not. Definitely it exists. If 0, 0, 0 exists as a zero vector, then that is a valid element under the vector space. No doubt about it. So considering that I have at RHS, I have 0, 0, 0. But now at LHS, what you already have? X1, Y1, Z1. Or say X, Y, and Z. Now, what are the three elements that you should be adding with respect to each of the positions of X, Y, and Z? If you have to get a 0, 0, 0, definitely that has to be minus X, which you have to add with past X and get a 0. It can be minus Y, which again you have to add with the plus Y and make it 0. And it will be minus Z, which again you have to add with plus Z and make it 0. Right? So you can see that all the properties are very much well-defined setup. It satisfies. Now option D we are checking. What is D? Set of all continuous functions on real number space R with a point-wise addition. Now, what is a continuous function? What is a continuous function in terms of calculus? I guess all of us know about it, that we have to check whether the left hand like limit with respect to that particular value where you want to check with the continuity, and the right hand limit where you want to check with the continuity at that very point should be equal. If it is equal, then we'll call it a continuous function. And the derivability or the differentiability was if you have to check with the left hand derivative at a particular point, whether it's equal to the right hand derivative at that very particular point or not. If that is also the case, then you call it a function which is a continuous as well as differentiable. Otherwise, if it is not differentiable, that is the left hand derivative is not equals to the right hand derivative, you call it only a continuous function. So that is the definition of a continuous function. Now, what was our question? Our question was a set of all continuous functions. So where the left hand limit and the right hand limit are same on set of real numbers. Shivalingam, I don't know. Let others confirm if it is a certain point of an problem at my end or not. If they are okay with the voice, okay. Okay with the voice. So
Voice is fine. Please check at your end. Voice is not a problem. Please check at your end.
yes, please rejoin.
Please proceed, ma'am. Please go ahead.
Please
Yeah.
rejoin. Yes, yes. So in that cases, so what you have to check, that you have to check whether a set of all continuous functions or real number with respect to a point-wise addition is a valid vector space or not. So let us define that V is a vector space, which is nothing but a function f such that it maps between a set of real numbers to another set of real numbers where fx is continuous. That is your vector space that you want to check whether it's a valid one or not. Now, addition you can do in this way. Say, for example, fx is a function and gx is a function. Then f plus g of x, whether it is
उनको
equals
नोट कर लेंगे, उन्हीं को एड्रेस करेंगे, उनको बोलेंगे भाई थोड़ी देर रुक जाओ, ठीक है ना, यहाँ ज्वाइन कर लो उस समय.
Okay. So f plus g of x, yes, it will be resolved.
नमिता हाँ जाके मैं ये करता हूँ, तब तक लिस्ट बनाता हूँ. हाँ लिस्ट बना दीजिए.
Professor Pilli, I think there is a
sorry ma'am, I'll tell.
Absolutely. Thank you, sir. So there has to be two functions on which we have to check. So when we want to check with a function, it has to be see just example. For example, we have taken two functions. When it was between a two 3D vectors, we have taken an example of a two vectors in order to justify that. So here, because we want to check with the function, it has to be an f and g where both we are considering as a continuous function and trying to check that whether that suffices the properties of a vector space or not. Okay, so f plus g of x should be f of x plus g of x. If that suffices, that is okay. And scalar multiplication, that is alpha times f of x should be alpha into f of x. That is, it should be a scalar multiplication. So addition closure, you can see also it happens. If you take any function f, it will satisfy this property. Then associativity and commutativity, that is also a thing. And additive inverse also exists because minus f of x is equals to minus of fx. Here the odd function and even function, nothing is given, so we can actually take it under consideration that this will happen. Okay, just for simplicity, let us assume that this happens. Let us not take an example or cases where because of the polynomial, if f is a polynomial of time, say only the odd powers of x, then this might be not the case, but for now let us consider that this thing also exists. Okay, and C is not correct. What was C? C was a set of all real numbers with multiplication at the operation. Now, very easily, if we have just this line, you should be able to understand that this is the correct option. Why? Because with multiplication, that is operation itself is multiplication. And can you get an like zero element here with respect to multiplication, which is an identity element as well? Meaning, if you have any random element, say x, and you perform multiplication, because I am doing it with respect to a multiplication operation. So say x dot. Now, can you get a zero over here? That will give you as a return something which is the similar element x. So x into 0 is equals to x. Is it ever possible? No, those things are never possible. So definitely that is why C is not correct, because I have not defined that what can be my set of, what are the constraints that I can include or not include in my vector space. So just for the example, say it will suffice from the zero vector issue where a vector space requires a zero element. We have seen it. Like that is a criteria of a vector space. It definitely should have a zero element existence. Just take the property number 3. It should definitely have a zero vector existence where 0 should be belonging to the vector space V. That is, it has to be another element. That element can be a singleton element, that can be a set, that can be a function, that can be anything. But definitely 0 should exist in the vector space in some way or the other, such that the another element u belonging to the vector space plus, if the addition operation is class, that identity or the zero vector should give you the same element. That is, it is the identity condition that should suffice. Okay, but with respect to a multiplication operation and with respect to real numbers, definitely that is not a case, because I do not have a x dot 1 is equals to x. So it will be, if it has to be like an identity element should be there. What is that identity element? If I ask you with respect to multiplication, the answer should be 1. Because any number multiplied by 1, whether it's a real number or a complex number or a say integer, it should be exactly 1, which should be multiplied with respect to that number in order to get the same number as the output. But it can never be 0, because 0 multiplied by anything is always 0, not the same number that we want to have. So even in discrete mathematics, we have like, if you are well aware of those things, group theory and all, you've seen the similar kind of concepts. So just like the same thing here also applies that under multiplication you cannot get a like zero vector existence. So obviously the zero vector axiom fails here. So option number 3 will not be a success, like an efficient or a say a successful vector space that you have, because it is not sufficing the requirement of a zero vector existence. Okay. Now this is a vector space. So in a nutshell, what we have seen here, that a vector space is just a fundamental concept of linear algebra where it has a certain properties that you have to suffice, and in quantum it has a like huge interpretation. What is the interpretation? Here we have seen it, that is it a vector means a direction as well as a magnitude. So your quantum state is defined as a vector where at every point of time, not necessarily only its amplitude changes, but also its direction of the phase and every parameter of it that corresponds to making it a vector entity that might also change. So that is why, for in order to understand quantum, we have to understand it that through with respect to a vector space, how it behaves. So it's not a constant one that you should be exploring about. Okay, even maybe for the same amplitude that you have, just like a scalar space, for example, say you have a same magnitude, then also if you have a two different direction for two different units, you call those two things as two different quantum states. That is why, because the direction or phase or amplitude, anything can imply different states, you actually have to understand the vector space concept. That is how it behaves. Okay, all these things explained. So next one is the state vector format and the linearly independent vector space. Okay. Now, before entering into the state vector and this thing, first of all, just to give you an idea, state vector is nothing but at every instance. So it cannot be that much of complex. Split the terms, state and a vector. So state has to be, for with respect to quantum, it has to be associated with certain quantum state. What is the difference between a classical and a quantum state? All of us have seen this thing in the last class, day 3. So first of all, a state vector has to represent certain state information with respect to a quantum state. Fine, final. Vector. What is the meaning of a vector? That is, it has to also have a certain kind of other parameters present into it in order to make it a state vector. Correct? Now, maybe vector also include a scalar, and vector can also like include a vector. You should be able to visualize it. If you do not have a momentum, or if you do not have a position parameter associated with a vector, then it behaves like a scalar. Otherwise, it will behave like a vector. Now, that kind of an in representation, that kind of simplicity we might have been using, but ultimately it is representing a vector, because quantum state, I have told you, it can be on and it can be off, and it can be any combination of on and off. It can be 70% of red, 30% of blue, 69% of red, 31% of blue, 20% of red, 80% of blue. So likewise, even if we have only say red and blue, so how much tilted it is towards what direction, that is its vector form, also defines its current location or current position or the way it behaves. So that is why your state vector representation is coming into picture. For example, your ket 0, which was represented with 1 and 0 in a column vector form, I will not explain it. I hope if to everyone this is very clear, for those who have attended the third day, that why ket 0, what is ket, and what is say 0, how it is represented, and why I am calling 1 0. You should be able to understand that 1 0 is a column vector which is in a 2 cross 1 form. Is that okay? So can I just assume that all of us are on the same bench with this particular notation in mind? Great. Thank you for confirming. So when I say a ket 0 is nothing but a 1 0, you have to assume that 1 0 is in a 2 cross 1 column vector representation, where 1 is on the top and 0 is on the bottom. Right? And say, for example, you have ket 1, where we represent that with a 2 cross 1 column vector with 0 and 1, where 0 is on the top and 1 is on the bottom. So both the two vectors, they also represent the ket vector very easily, because state of the quantum system to be in the position 0, and 0, 1 represent the state of the quantum vector where we try to represent the state 0, 1. So both are state vectors. Now comes a very important point, that how many of them, or whether these two also are linearly independent or not. So now the concept is from the linear algebra. It has nothing to do with the quantum mechanics or quantum mathematics. So any one of you tell me that what do you mean by a linearly independent vector, or what is the meaning of linear independence with respect to a matrix or a determinant versus a linear dependence between two vectors? At least one or two points that so that we can proceed with that. Delta A0 is equals delta of A, that is determinant of A is equals to 0. You have told it. So what is the meaning of it? If determinant of an like matrix, if that is 0, so what do we mean by that? This is just like output that you are doing. We can show them linear dependence. Yes. So what is the interpretation of it? How those two things are dependent? Now, if we have a matrix, say for example, I have a 3x3 matrix. Can any one of you refer the like language of rank with respect to rank of a matrix with respect to the linear independence or dependence? Any one of you? Can you relate these things? At least one row is a linear combination of others. Great. Two vectors are connected with a scalar quantity. Full rank for linear independence. Okay. Something similar I'm getting. So if I have to be like it fill up the space, number of linearly independent vectors in matrix is rank. Absolutely, that is another way of defining rank. So absolutely, let us just take the last point where someone of you mentioned that rank is nothing but the number of linearly independent vectors in that matrix. So what do I mean by that? What I mean is, again, some of you has explained that, okay, with respect to a few vectors in that matrix, I should be able to regenerate the other rows of that matrix. So that is called of a dependency. If we can find it, then we call it a linearly dependent one. And in those cases, what will happen? Your determinant of that matrix will be 0. So if you have a 3x3 or a 4x4 matrix, say, and if you are getting a determinant of that matrix as 0, then what definitely you can infer? You can infer that definitely the number of independent rows is not equals to 4 for a 4x4 matrix. It has to be less than equals to, or strictly less than 4, not less than equals to, because your determinant is already 0. So it's strictly less than 4. Now you have to check whether it's strictly less than 3 or it's equal to 3. Likewise, all those 3x3 submatrices you have to take, and you have to check whether that determinant is 0 or not. That was a kind of a concept. So the similar concept here also exists, where number of linear independence means we have to check that how many rows of them are completely independent of each other. That is, they cannot be regenerated using some other rows or other columns of that particular matrix. Considering, I'm not considering any row reduced equal form or anything like that, from a very random matrix. Say for example, I have 1 2 3 in the first row. Okay, it's a 3x3 matrix. In the second row, I have, say for example, 2 4 6. Then my first row and second row, they will be linearly independent. Why? because I will be going to that, because the second row can be exactly expressed as a scalar like multiplication or multiplied product of the first row. Just multiplied by 2, you will be getting, say 2 is the scalar quantity that I'm multiplying with every element of row 1 in order to get every element of row 2. So that is kind of a linear dependency. But in quantum, we do not actually rely on those things. What we believe it, every state vector, what do I refer by a state vector? Either it's a 0, 1 or a 1, 0 in a column vector, or a 1, 0, 0, 0, which corresponds to 0, 0, or every those of the state vectors. That is a quantum state representation in the column vector format. Whenever we referring those, it has to be very well are linearly independent things. That is, it should be non-redundant. We should not be able to regenerate any of the other row or any of the other information. Row or column is just a like gimmick. So no other information we should be able to interpret if we have only those set of informations available. Okay, that has to be something that we need to follow. So in quantum mechanics, linearly independent vectors are the essential building blocks of quantum states. A set of such vectors forms a basis, a fundamental set that describes everything possible in the system. This is a fundamental unit. You cannot further reduce it. It is a most reduced form. Now, set of vectors forms a basis. Means, for an example of a 1-qubit quantum system, where number of qubit is 1, it's a quantum system. How many states are possible here? 2 states, because I have a 1-qubit system. So it's 2 to the power of 1 number of states. That is an on and an off, right? That is a 0 and a 1. So 0 means basically 1 0 into vector form, and 1 0 0 1 means get 1. So 1 0 and 0 1 together will form one basis corresponding to a 1-qubit quantum system. Similarly, for a 2-qubit quantum system, we call 1 0 0 0, comma 0 1 0 0, comma 0 0 1 0, comma 0 0 0 1. All these 4 vectors we call as one basis corresponding to a 2-qubit quantum system. Is this okay? Are you just understanding the terminologies at least? A set of the vectors, independent vectors, they form a basis for a quantum state. Great. Now, for example, if we have a 3-qubit, all the 8 state vectors, starting from 1, then all 0, 2, till the last point where it's all zeros first, then ending with a 1. Yes. No, I'm not using whiteboard yet. Not using any whiteboard. Everything is put on the slide and few other things that I'm explaining verbally. Okay. So again, in order to start from the very basics, so describing a quantum state is nothing but a roll of state vectors, where every object in our world has a unique identity. If you have seen the Matrix movie, you will be having a very great understanding of the same concept. You can see that everyone, including you, me, tree, pond, whatever you see around us, everything is nothing but in a matrix way, where everything like a 0 or a 1 value that will ultimately be able to regenerate your entire existence uniquely. So every object in our world has a unique identity. Similarly, in quantum mechanics, DNA or quantum slide where you are getting the, oh yes, I'm on the slide. Yes. So just by meaning of DNA of quantum system is nothing related to DNA computing. I just try to mention that it's the fundamental or core of any quantum system. So that is a state vector and linear independence. So every object in our world has a unique identity. Similarly, in quantum mechanics, every quantum system can be described by a state vector. I hope right now you are able to just pick up every word and try to map how it behaves mathematically. Every quantum system described by a state vector, so which captures all its possible behaviors. Again, 1 0 0 0 0 1 0 0. Now you know how the behavior changes. Even 1 1 0 0, what does it mean? 1 1 1 1, what does it mean? I hope you are able to predict all its individual behaviors with respect to its current state vector of that particular quantum state. So these state vectors do not live in any ordinary space, but rather in a very abstract mathematical space of the quantum mechanics. So imagine you are designing a puzzle and you need to set a unique building block. If you can create any shape by just or any row or any column or any information. Okay? By just combining a set of these blocks or row or column or information, then those row or column or blocks are called linearly independent rows or columns or blocks, where none of them is redundant. And that is the rank of that particular matrix. Okay. So here a 3-qubit system should have a rank of 3 only. It cannot be 2 or anywhere less than 3. And in quantum mechanics, linearly independent vectors are the essential or fundamental building blocks of quantum states. A set of such vectors forms a basis, a fundamental set that describes everything possible within the system. And for quantum computers, choosing the right basis allows us to manipulate the quantum information in a way that maximizes the computing power. Again, this line is very tricky. It has no relation with the representation. It has to be somewhere related with the how you encode it so that you can get the maximum benefit. That is what it is aiming to say. For example, for a TSP, traveling salesman problem, what you should be encoding? Maybe by encoding age, what you can get in with respect to the quantum supremacy or quantum advantage. Hope right now you at least in a very nutshell know what is the difference between a supremacy and an advantage. So if I encode for a traveling salesman problem, say for example, nodes of the graph, you might get a speed up of say 40%. For example, I'm just telling, if you encode it, the age into it, you might get a speed up of say 25%. But if you are able to encode the paths into the quantum registers itself, the entire path or entire Hamiltonian cycle, or all the possible cycles you are able to encode, say 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. Likewise, the entire ham cycle you are able to encode it. If you are able to do that, maybe you will be getting a speed up of say 45%. So here is the meaning that choosing the right basis allows you to manipulate the quantum information in a way that maximizes the computing power of quantum, yielding the maximum speed up, yielding the maximum efficiency of quantum computation. Now, some of the mathematics of it. So, linearly independent set of vectors. So, understanding linear independence is very crucial in quantum, since quantum states form a vector spaces over a complex set of complex numbers. So, a set of vectors v1, v2, v3, vn in a vector space V is linearly dependent if there exists this symbol. I hope all of you know it. Don't need to explain it. This like mirror image of E, capital E. This is a there exists symbol. If there exist scalars, say C1, C2, Cn, not all of them are 0, such that C1 times V1 plus C2 times V2 plus C3 times V3, likewise Cn times Vn should be equals to 0. That is, if it is not all 0, that is C1, C2, C3, C1 equals to C2 equals to C3 equals to up to equals to Cn is not 0, then we call it a linearly dependent vector. But if all the values are 0, then it is a linearly independent vectors. This is a way of mathematically describing through the definitions of linearly independent sets. So a set of linearly independent vectors span a vector space uniquely, meaning each vector in the space can be written as a unique linear combination of these basis states. Okay, if we have it with respect to a real number, say two-dimensional real number R square, where say v1 is one of the vector which is 1 0, which is ket 0, and v2 is another one which is a 0 1, which is ket 1. To check linear independence, assume c1 times 1 0 plus c2 times 0 1 is equals to 0. That is our condition. C1 v1 plus c2 v2 plus up to it should be 0. So I'm assuming that c1 times this v1 which is 1 0 plus c2 times this v2 which is 0 1 is equals to 0. Just multiply it with the 1 and the 0, it is C1, C2 equal to 0, 0. So right now from these lines, C1, C2 is equals to 0, 0. You can infer that the only solution that can exist here is C1 and C2, both are having the values 0. Right? So if that is the case, that is if I get all the scalar values to be equal to 0, none of them are non-zero values, then what we can infer from this? We can infer that it's a perfect example of a linearly independent set of vectors or set of basis set of state vectors which is forming the basis. Okay. Now say another example, just in order to say that, okay, it's not a linearly independent one, it's a dependent one. Say I have a certain vectors like v1, 1, 2, 3, v2, 2, 4, 6, and v3, 1, 1, 1. Obviously, from these only this line, you can check that it's not really linearly independent because 2, 4, 6 is nothing but the scalar multiplication of 1, 2, 3. Just formally, if we have to show the or demonstrate the mathematical proof, check if there exists a non-zero scalar C1, C2, C3 such that this equation is satisfied. So C1 times V1 plus C2 times V2 plus C3 times V3 should be equals to 0, 0, 0. Just multiply them like C1 plus 2C2 plus C3 is equals to 0. Then 2C1 plus 4C2 plus C3 is equals to 0. Similarly, 3C1 plus 6C2 plus C3 equals to 0. If you try to solve it, there are 3 equations and 3 unknowns. Definitely we are able to solve that and find the exact solution. If you do that, we'll check that we find a non-trivial solutions. Trivial means a 0, 0, 0. Non-trivial means any of the values are not 0. So if you solve it, you will be getting C1 is equals to 1, C2 is equals to 0.5 minus, and C3 is equals to 0. Meaning that these vectors are not linearly independent, they are linearly dependent vectors. Now, the question is why linear dependence is very bad. Because first, they do not provide you the unique representation, and it is very difficult for a quantum, because ultimately at the time we will be measuring it, you should be able to, or while you are encoding it, for both the cases. Okay, so the way you are encoding, that is how the time evolution will take place. Now, based on the time evolution that is taking place through the Hamiltonian and the Schrodinger equation that we have seen in the earlier class, accordingly, at some point of time, you are just about to begin your measurement. So what you are holding just before your measurement is the way you have encoded it. That is how it has actually propagated through the time space, for example. Now, in that particular scenario, on that instance, if there is any ambiguity in understanding or going back or retracing what was your initial encoding, or what was the initial information that you wanted to encode through your quantum algorithm, that should pop up as a solution. If that there is any ambiguity, then you cannot do that. And also, we have seen in the very first class that irreversibility is a big challenge for a classical system. So, what was the fundamental requirement for our quantum system? That is, it has to be perfectly reversible. At any point, we should be able, if we just redo another operation or undo some operation, we should be able to like interpret a one-on-one mapping between the input and an output. Just remember our AND gate example. From a 0, we cannot tell what was the input, whether it was 0, 1 or a 0, 0 or a 1, 0. Similarly, for a OR gate, we were unable to tell earlier if we have an output 1. So we are unable to map it to exactly one input, because it could be, one could correspond for a OR gate either to 0, 1 or to 1, 1 or to 1, 0. So these kind of ambiguities we cannot allow, because quantum only follows the reversibility logic. So that is why linear dependence is a perfectly bad scenario for a quantum one. Yes, but only the NOT gate, if you remember, also just hold that thing in your mind, that NOT gate was one of the only gates which you have in classical that behaves quantumly, because it follows the reversibility logic. Because if you have an output 0, you can tell that my input was 1. If you have an output 1, you can tell your input was 0, right? Input 0 and 1 means a VCC. You have a very low value that corresponds to 0 and a very high value that corresponds to 1, but at least you are able to predict that through a NOT gate. So NOT is only classical gate which behaves reversibly. But in quantum, every gate, everything that we were discussing in the next classes also, you can see it, everything is perfectly reversible. Okay. So that is why there is no energy loss or information loss or energy dissipation that happens. That KT into times ln2, that will not happen at every step, because at every step, no matter where you are, till the time you measure it, you should be able to go back to the earlier step. By just redoing the same set of operations in the reverse way, you are actually able to trace back or go back to the earlier step. Okay. So that was the thing. That is why we all here aim for a linearly independent vectors. So they are very finely related to each other. And the second point is why it is very bad. That is, a quantum computation requires independent basis states. Yes, but because if you have a linearly dependent one, it will not work. Okay, now 1, 0 and 0, the same thing. Right. So far we have discussed the fundamentals or way we actually work with this mathematically, where we have checked the vector space, as well as we have checked the linearly independent set of vectors and what are their interpretations with respect to like quantum. Why are they very important, and what we are aiming for, and how also, if you are given any questions like what defines this to be justified or applicable in a quantum setup, I hope you are able to do that. If you are given such a set of like matrices like this, just as you can see in the screen, definitely it is not something where you can proceed with quantumly. Then you have to like extract the minimum information, which again you have to like map it through the basis states, right? Or form a new basis with respect to this information. That kind of an extraction you have to do. Now, the third mathematical one, which is also very important, is with respect to the inner product. So an inner product is a function that takes two vectors and returns a scalar. Satisfying two like matrices, it generalizes the dot product. Okay. Now, with an example, we will actually see it very easy. But mathematically, what it measures, it measures the similarity in quantum mechanics. So how close, now focus, we are talking about inner product, then we will go to inner product space, then we will understand in a very easy way what's the Hilbert space. That is our target, where we are like trying to go to, so that we can enter into block sphere and understand the real positional aspects of the quantum states also in that three-dimensional vector space. That is our agenda in today's and tomorrow's class altogether. So how close are two quantum states? In everyday life, we compare things based on the similarity, that how close the two songs sound, how similar two faces look like. In quantum mechanics, we also need a way to measure that how similar two quantum states are. And this is where we need the concept of an inner product to come into picture. So imagine you are in a dark room with two light sources. If two lights shine in completely different directions, they do not never interfere. But if they shine in similar direction, they overlap and mix. So this is the essence of the inner product. It tells us how much two quantum states really do overlap with each other. And an inner product space is one where this concept of similarity is very well defined. In quantum computing, this helps in distinguishing the quantum states, performing quantum measurements, and even designing absolutely the angle also, and even designing the quantum algorithms. So this is in a very fundamental level. Maybe we will be doing, because right now it's very well developed, so we will be doing a lot of operators and all. But fundamentally, this is how we used to initially investigate that how close they are or how they are differing, so that you are able to understand that which quantum gates you should be applying for, depending on what exactly your requirement is. So here the inner product concept is coming into picture. So for a vector space, just a minute, for a vector space, say for example, it is nothing but a function. You can see a opening bracket, a dot, comma, closing dot, closing bracket, where in places of dots, you have to fill it with certain values, such that V cross V is mapped to a complex vector space satisfying three properties. But what is the first property? That is a conjugate symmetry property. That is VW within an inner product form should be equals to WV. Linearity in one first argument, that is AV plus BU. A and B are nothing but scalars, should be comma W should be equals to A, then inner product of VW plus B, inner product of UW. And positive definiteness, that is V and V, when both the elements are same, they should be greater equals to 0, and V and V will be 0. IFF, that is if and only if V is equals to 0. That is vice versa. If V is 0, then V comma V will be equals to 0. And if V comma V is equals to 0, then we can infer that V is also equals to 0. Now with several three examples, we'll actually verify that whether the inner product properties will justify the axioms or not. That is our target. So say for example, V is 1 and I, and W is 2 and 3I. You can also do the calculations by your own and check as and when I proceed to the slides. So in our product, we want to compute, which is VW. There's nothing but like sigma I, VI conjugate WI. The VI bar, this is a representation of a complex conjugate of the IF component of V. Now, if you know, for a real number, it's always the same number that comes as a complex conjugate. And if it is, say, some imaginary number, say 2 plus 3i, the complex conjugate will be 2 minus 3i. If it is 3i, it will be minus 3i. If it is I, it will be minus the 3i. If it is minus I, it will be I. Likewise, we calculate the complex conjugate. But if it is only, if it is like a, only just a like integer or real number, it will be exactly the same number. So considering all those things, that we know these things. So if V is V1, V2, and W is W1, W2. So what will be V and W? In this formula, it will be 1 bar times 2 plus I bar times 3I. I hope you know that it is this from the same thing we are getting. That is V bar V1 bar W1 plus V2 bar W2. So V1 is 1. So V1 bar is 1 bar dot W1, which is 2. W1, which is 2 here from I'm getting it, plus V2 bar, which is I is V2. V1, V2, it is the form. So I is V2. Then I bar times W2, that is 3I. Just calculate it. So 1 bar is 1 dot 2 plus I bar is minus dot 3I. So it's basically 3 minus of 3 into I square. I square value is minus 1. So likewise, we're getting 5. So the left hand side is actually 5. Now compute WV. You have to compute. See, LHS is VW. in inner product. Then right hand side is WV, then a complex conjugate of that. So WV is equals to the similar way 2 bar times 1 plus 3I bar times I. So it's 2 dot 1 plus minus 3I dot I is equals to 5. And 5 itself is a real number whose complex conjugate is the same number. So we can definitely verify that VW is equals to WV with a complex conjugate. So conjugate symmetry holds for a inner vector space. Now, the second property that we have to check, that is a linearity. The second property, just check this one, 2. Property number 2, the linearity in the first argument. We have to check this one. So, AV plus BU, comma W should be A, then inner product of VW plus B into inner product of UW. Okay. Just one thing, right now it's already 3. So just give me 5 more minutes maybe. If that would work well, then I will just complete the verification of these last 2 points, 2 and 3. Then maybe by 3, 5, we will take a break for 5 minutes. If that is okay, then we can do that. Otherwise, if it is strictly like at 3, we can take a break as well.
Please go ahead, madam. Whenever you want to
Yes,
give a break, you give.
just give me 5 minutes. Just let me complete the verification for 2 and 3, then I'll give a break. Okay. So this is the inner product form that we want to now verify. Okay, for that, how to easily do that? Proof by contradiction. If it is valid for all the cases, then we'll call it as a valid thing, valid argument. So say for example, V is 1, 2, U is 3, 4, and W is 5, 6. Any random values we have taken. And take say for example, A is a scalar and B is another scalar. So both the values are 2 and 3. So left hand side we will be calculating individually. Then right hand side we will calculating individually and check whether both the things are left hand side and right hand side both are equal or not. So LHS is AV plus BW, comma W. So first let us calculate AV plus BW. A is just a scalar. It's a scalar multiplication with respect to a matrix. So it's basically this 11, 16 times 5 and 6, which comes as a result of AV plus BW and W. So now just calculate the inner product. It's W times 5 bar plus 16 times 6 bar. 5 bar and 6 bar are 5 and 6 itself. So it's 11.5 plus 16.6, which is 151. Okay. I do not know. Maybe you are asked this kind of questions as well in the exam. I am not sure of it, but definitely these kind of questions might ask from quantum physics or these concepts. And then the second one is VW. Individually, you have to calculate this one for the right hand side. It's 1.5 bar plus 2.6 bar, which is 17. And UW, that is associated factor with B, is UW. So it's 3.5 bar plus 4.6 bar, which is 39. So RHS, just compute both the things together. So it's 2.17 plus 3.39, which is 151. So we can also verify the second property also holds. You just, for these things, you just need to calculate or just need to know how to calculate the inner product. And see, for real numbers, you might not see it's exactly like V1 dot W1 plus V2 dot W2 as a formula for V comma W as an inner product form. Just remember, it is only true in case of a real number. If it is an imaginary number associated there anywhere, then you have to calculate it accordingly. Okay, don't take the same value. It's V1 bar dot W1. That is how you should be calculating. So when it's V comma W, it's V1 bar dot W1 plus V2 bar dot W2. If it is W comma V, then it's W1 bar dot V1 plus W2 bar dot V2. Only if all the values are real numbers, there is no imaginary part, you can also consider as V1 W1 plus V2 W2. It only holds for inner product when you have a same value. You do not have a imaginary value, you only have a real numbers. Okay, just keep that thing in mind. And third property, what we had, that is a positive definiteness. That is, you have to now choose two similar elements, V and V, and that inner product you have to calculate and check whether that is greater or equals to 0 or not. And if you take the value 0, whether it's exactly 0 or not. That is what we are aiming for. So say for example, we have taken 3 and 4. You can also take say 3 and 4i. That is absolutely your choice. Now just check the values. It is V comma V in our product you want to calculate. That is 34.34. That is 3 bar dot 3 plus 4 bar dot 4. That is 3.3 plus 4.4. That is 9 plus 16, which is 25, which is your V comma V in an inner product form. And 25 is a number which is greater or equals to 0. So your first property is like justified. Second property is when it is exactly 0. If you obviously now you're understanding, if your V is 0, then V comma V will exactly be 0. So your second thing or second sub property under positive definiteness, that also is satisfied. Okay, that is the thing for the inner product. Now next we will enter into Hilbert's space. This multiplication. Okay, your question, I think it is yes, maybe. Just one, two questions I want to answer here. Principal component analysis is just the way so that you can reduce the number of columns in order to make it in a bit in a reduced form. So primarily it is used for a hybrid computing where you have a classical and a quantum ones. But this is very basic. But of course, if you have to encode it, all the pre-processing I'm not considering here. I'm just at a position where I will just do a feasibility check that okay, so I am able to encode you as a quantum computer if you come with a linearly independent basis vectors mapping only. So as a quantum computer, I verify in accordance to that. Now, before that, you might apply PCA, you might apply some other logic. That is completely up to you. But those set of like auto tuning you have to do if you want to make it feasible to be run or to be implemented using a quantum computer. So as a quantum computer, I will validate your encoding only if it comes in the form of a linearly independent set of basis vectors only. In that way only, I will able to like acknowledge it, okay, and allow it to be run on my system or setting. That is the thing. Okay. Thank you, Mikin sir. Okay, now it's 3-6. Now it's up to sir, to you, Pilli sir. I'm giving just a 5 minutes break. So it's 3-6 or consider it 3-7. So we'll come start again at 3-12.
Yes, ma'am.
Okay. Thank you, everyone. Just a small break, then again we'll come back.
Yeah, can you unshare your slides, ma'am? Just.
Sure.
Yeah, others can take a break. For those who have doubts on things like Canvas and all, just let me show you some of these things. So this was a email which was sent. So you would have received. Let me share that. So this is a kind of an email which you got. So you will have to click on this link or you will have to copy this part of the content, right? So don't include the where you have the things that are there. Don't take the brackets along with you, right? Leave the brackets, only the content that is there inside, right? So you take it and then you paste it and then you will get that. Okay. So then you will, once you click on this, you will get an email which will be coming from WebEx, right? So you will have to look at that where the response will be in that lines, that you will get a WebEx mail, right? And the WebEx link will be somewhere here where registration approved. This is the kind of mail that you will get, right? Are you able to see that? It's not yet come, right? 1 minute. Yeah. You go back. It will take some time, I think. Yeah, this kind of a mail will come, right? So in that, you will see that you can join the webinar, right? This is the process that has to happen. So the link is shared in your respective WhatsApp groups, and you can check that. And then now you just have to click it. Then you will get a confirmation mail from WebEx, right? So the WebEx title will be something like this. It will come from EICT Academy. Okay, as I am showing now, it is this is yesterday's mail. Yeah, this is the first one that has happened. So the title will be something like this: registration approved from WebEx. It shows that the mail has come from EICT Academy here, right? It is showing EICT Academy here, but actually it is coming from messenger@webex.com. You can see the site, right? So this is what. So please understand that because you are already here, I think this is what has to be done. If you can explain to your friends who are still struggling or colleagues who are struggling, you can explain to them. So this is what has to happen, right? And similarly, if you are looking at Canvas also, right? So if you go to Canvas, so let me share the screen. Let me share the screen itself. So this is a kind of canvas. So first you create your account. That is my suggestion. Okay. So create your canvas, right? So create your canvas. First create some ID. Okay. If you have registered with some ID, in my case, I have registered with espilly@mnit.ac.in. So I have created that. Okay, so this is the ID that I have logged in with. So you can look at that. So that ID can be there. One minute.
Sorry, sir. Sorry,
Right,
sorry.
right. No
Okay,
problem.
okay.
No problem. 1 minute.
1 minute.
Yeah. So you are able to see this whole thing, right? Sorry, we are on. There's a lag. Yeah. So this is something that you can look at. So with this ID, maybe if you don't have an ID, whatever ID you have given as a registration, that ID you please include here. Okay. And then you can create a login, right? So what will happen actually is when you look at that thing, you just go and search for instructor. Okay. In structure, there will be a course invitation. So I've just searched for instructor. I've gone to my email ID and I just search instructor. Instructor is the organization where which has given out that. So you'll have that course invitation, right? So you go to the course invitation, right? So there it will show you that email ID that you want to register. This is registered with us. Okay, it's showing the email ID here. When I open that email, it is showing that email. This is the email which I have registered. This is the email which I have registered for this course. So I will just have to say get started. Okay, once I've created my ID with this, and I'll go and I'll just say get started, right? Then I will say get started. Get started will take me to the same window, that is Canvas, because I've already created my ID. Okay, as you see now, it will take me to Canvas. Well, I'm just clicking on get started. It's taking me to Canvas. And now I have opened. So I will go back and enter that same ID which I created earlier, if that is the same ID. Okay, and I will say login. So I'm entering that details and I'm entering that same details and I'll call you back. So it will directly take you to the course. No registration code should be asked. If you are entering a different email ID, the registration code will be asked. Now somebody asked me where are the video recordings? Click on modules. Click on modules. And you will be able to see the lecture recordings, right? Go to modules. Are you able to see modules? And then you are able to see the recordings. The other part is go to files. Okay, below modules are files. So I'm clicking on files. Go to files. Go to files and see on the files, you will be able to see two types of material that is there. Two types of materials. Under quantum technologies, you will see lectures and you will see WebEx attendance. Okay, so if you go and click on the lecture material, okay, you will be able to see the slides. If you click on the lecture material, you will be able to see the slides, or you will be able to see lecture slides again. Again, you will have to click another window. There you will be able to see lecture slides. And the attendance is also mentioned there below that WebEx attendance. Recordings are put in this thing. So I hope you are clear. If there is still anything, we will close the WhatsApp group. There are two WhatsApp groups running, one for MNIT Jaipur. Similarly, all other academies, if they don't have a WhatsApp group, please see, don't go to invalid code. That's what I'm saying. Create a Canvas login. And after you create a Canvas login, come to this email ID which you received from our academy. Click on that. Then it will not ask an invalid code. Right? So code is asking means you are doing a wrong process. I can explain you 100 times, but we want you to come on Canvas. Because if you are a registered participant only, then you will be able to come on that. Recordings, nothing is mentioned in recordings. I told you modules. Click on modules. You will be able to see the recordings. Click on modules. Modules are there upstairs, below assignments. Modules is there. Click on modules. You will be able to see the recordings. I have just clicked on modules. It will take some time. I have clicked on modules. It is now going to show all the recordings, right? Are you able to see? Yeah, so we will continue with ma'am. If there are still any doubts, I'll try to give you, yeah, quizzes and assignments. We have, they are coming. Once we, this is the, what do you say, admin module, admin dashboard. So these are more, I will be able to see more. Once I post the quizzes, then only you will be able to see. Is that okay? So please don't worry. We are also encouraging you to use Canvas, which you can use for running your courses also, collect your assignments, do the grades and all, conduct online exams. So hopefully we are doing parallel. We are also learning. Yeah, WhatsApp group, contact your respective academy. If you are registered with MNIT Jaipur, please write to me. I will add you in the group, or I'll send you the link, right? The first learning which is going on, I will also encourage you, right? Thank you. Over to Nivedita ma'am.
Yes, sir. Thank you, everyone. So, again, let me share my screen. Yes. Is my slide visible? Okay. Thank you. Thank you for confirming. Yes. So, so we ended here, where we have done. Just a quick recap what we have done today. We have, and the last day, what's continuity. We have seen the quantum state representation. Then for that, we had like a column vector representation, bracket notation, a brief of understanding of that. We had understood the differences between a classical and a quantum states. We have seen that there are certain features that is allowed only for a quantum state, which is not allowed if we want to do any manipulation on the classical states. Now, from that thing, from that concept of states, we came into the concept of a vector space. And every sort of these kind of quantum states or a classical states, we can think of to be mapped into a vector space. Slides not showing. Yeah, Hilbert space slide should be visible to all of you. So I have not done any navigation with the slides yet. but it should be visible to all of you.
Slides are visible. Yes, please.
Okay, yes. So after that, we have seen that what is a vector space and what are the criteria that satisfies any random like vectors to be a part of the vector space. Then we have seen the linearly independent vectors and what is the concept of an inner product. Okay, and inner product corresponds to the inner product space. Now from that thing, that was the last part. From that thing, we have right now in another theoretical one. I will put very less amount of time here because again in the next class, tomorrow's class, we will start with again the Hilbert space and some of the other things. So in that way, I will just try to balance the concept so that you have a better understanding, smart the concepts, so that with the physics part you have a real application oriented viewpoint as well for quantums. So Mohammed, just try to rejoin. I think it's your problem somewhere in your system. So Hilbert space is just kind of an advancement of the inner product space where we believe that it's a vast and complete universe of quantum states. For example, let me just story tell you something. Imagine if you have a library where every possible book that could ever be written that exists. Now, no matter how many books you take from the shelves, there will always be more to explore. Okay, so just think of an infinite series where you do not know that where exactly, maybe 0.3 times something is a element of that series, 0.03, 0.003, 0.31, anything that we want, we basically can do it in the yes, I will explain it in a product and outer product form. So anything that you can think of, you should be able to theoretically represent it in that particular space. That theoretical space where you have a provision to fit into the infinite collection of states is known as the Hilbert space. It is a special kind of an inner product space where that you consider it to be complete, meaning that it includes even the limits of infinite sequences of books or quantum states. It is able to theoretically, as if it is able to theoretically map anything that you can think of in form of a quantum state. It is able to do that. For example, say for example, right now, a very basic example I'll give you. You have a clock where it is enabled to do a certain kind of a division of time units in terms of number of hours, right? It can do that. Can it do that in terms of minutes? Yes, it can do that as well. Can it do it in terms of hours? Yes. Can we think it of like even beyond hours? Even beyond seconds. So like hours, minutes, and seconds. Can we go beyond seconds? Yes, we can do that. If we want to divide it with respect to some, say, milliseconds, we can again do that. With respect to after millisecond, if every millisecond we need to further divide it and put it a name or try to quantize that fine, the finest of the units. Can you do that? Yes, theoretically we are able to do that. So that kind of a space where no matter what, everything, if you are able to divide it and put it in form of a quantized form, you are able to make it in a distinguished status. You can actually assign certain kind of a status of a state. If you are able to do that, that is called a Hilbert space. So it's kind of a vector space that is thought of to be complete. And quantum mechanics relies on Hilbert spaces because quantum states often require some infinite precision. Even if we approximate a quantum wave with a sum of simpler wave, we always stay within the rules of the quantum physics. And also, the very basic, this intuition you can actually visualize if you check once today, if you want to, the quantum Fourier transformation. Just go to IBM Qiskit, just try to check, or some, you can also visit certain kind of like YouTube as well. Just check that how the QFT simulation works. In Qiskit also, it's a very well demonstrated factor where you can check that if you increase it, like the order of the Fourier transformation, you can see the minutely divided quantum states into pixels. Okay, so basically, that is the fine essence of it. Now, how it is very helpful, the Hilbert space concept. If I have a 2-qubit quantum state, so entire Hilbert space I will divide into two things. If I have a 2 state, that is a 1-qubit Hilbert space. So it will be an on and off. Only 2 states I will be having. If I want to divide it into 4 states, what I will be doing? I will increase simply the number of qubit from 1 to 2. Then I will be having 4 states. Now, how these 4 states will come into picture? I have one 3-dimensional ball. I am talking about this thing from the last place. I have only one 3D ball, where on each of the surface you can put a certain quantum state. Now, if from 2 states I want to design 4 states, then I will simply increase the number of qubits and make it from 1 to 2. So 2 qubit will have 4 states. So out of the 0 and 1, it will now be 0 will be further subdivided into 0 and 1, and 1 will be further subdivided into 0 and 1. Likewise, it will be 0, 0 and 0, 1. Similarly, 1 will also be 1 times 0 and 1 product 1. So now you will be having 4 states. Your 0 right now will be divided into 0, 0 and 0, 1. And your 1 will right now be divided into 1, 0 and 1, 1. Now you have 4 states. Now say for example, right now you aim for some more number of states. And you want to fit all those states into your quantum ball itself, a 3D ball. So you will be increasing one more qubit. Now, if you increase one more qubit, that qubit itself can be 0 and a 1. So right now what you have, I will do the mathematics of Hilbert space in our tomorrow's class. It is just at least try to visualize, at least try to have that idea in your mind that right now where we are standing with 4 states. What are the 4 states? 0, 0, 0, 1, 1, 0, 1, 1. And I have 2 qubits for that. Right now I am aiming for some increased number of states. So for that, what do I need to do? I need to increase the number of qubit. Say, for example, I have now introduced a third qubit into picture, which is able to encode only 0 and 1. So it's a product between the earlier one, which was 0, 0, 0, 1, 1, 0, 1, 1 times the new qubit state, which is 0 and 1. So whenever I do a product or a tensor product between 2 vectors, what I should be able to get? 0, 0 times 0, then 0, 0 times 1, that is 0, 0, 0 and 0, 0, 1. Comma 0 that 0 1 initially in the first subset I'm taking 0 1, from second subset it can come 0, then 0 1 0, comma from first it can be 0 1, and from second 1 is coming, so 0 1 1. So from second I am getting 0 1 0 0 1 1. Similarly from third I can get 1 0, then from the second qubit 0 will come, so 1 0 0 and 1 0 1 will come, and last it was 0 1 1 in the first subset, so from the second one 0 will come, and from the second one 1 will come. So likewise, just by increasing a more number of qubits, we can actually break the space into infinitely similar smaller subspaces, where each of the space will correspond to the increased number of quantum states, and that we are able to represent. So that is basically called a Hilbert space. So Hilbert space is very much useful for quantum space, whereby increasing the number of qubits, we increase the size of the states that can be represented in that abstract space. So it's basically an abstract one which we were complete. Now, just one thing, just keep it in mind. In quantum, it's very theoretical, Hilbert space concept. In practical, there are a lot of factors that you have to consider. What are the factors? That is there any practical limitations on that 3-dimensional space, even if we are able to encode it or plot some value of a quantum state? Say, for example, you have 5 qubit you have introduced, or say 50 qubit. So all those 0, 0, 0, 2 to the power 50 number of states you will be getting theoretically. But the real challenge is, are you able to get in your measurement exactly those states, those many states, because they have a very small, very minutely small deviation. They have a very less maybe deviation in terms of a direction, or in terms of a phase, or in terms of an amplitude. Are you really able to even extract those finite or very fine-tuned information in a finite format? Are we able to quantize it in that level? That is a big challenge, because whenever we are measuring something, we are measuring it with our macroscopic world. So we should be able to understand it and manipulate it in the macroscopic level as well. Those are certain real challenges that we have. So how this issue can be resolved in the real essence? It can be resolved once we have a very fine-tuned commercially available quantum computer where there is a very less amount of error, no decoherence almost. Decoherence is what I explained it. Just for those who are attending this class as a very first class, decoherence is the like enemy of quantum computation. It actually decohers your current state decohers with respect to time. A very small example, maybe you have learned something today and we have our exam say after 4 months, versus you have learned something today and you have an exam on tomorrow. Definitely your performance level will vary. If you are an attentive listener for all these 2 hour session for today, definitely your performance in tomorrow versus in after 4 months will vary. Why your 4 months it will vary, and how it will vary? You will like continuously through like different events of your life, a lot of other engagements, it will try to get very diminished with courses of time. So ultimately, if you do not try put a repeater, or if you do not like in between try to study it or do a recap, it will definitely be very less amount of information that will be kept to your memory. That's a normal way we all think. Similar things happen with quantum as well. If you do not apply any repeater or something, if today you have some information, or say at 10 a.m. you have some information, that quantum state you want to manipulate at 10:30, definitely it has a greater chances of losing that information altogether, or it will have some distorted form of energy. So all those things you have to keep it in mind. This is fundamentally called as decoherence. So while even you are doing it theoretically, that you have a Hilbert space where you have a lot of states into it, you can encode all the states together. There's an exponential speed up. You can achieve quantum supremacy. All those stuff. You have to think of the practical challenges or the engineering challenges as well. But again, all of our discussion right now is not really dependent on the hardware yet. So what we are believing, that if we are able to do that, we can actually able to encode exponential number of states into it. And our ability to infinitely plot and put any quantum state into a vector space, that kind of a vector space is known as a Hilbert space. So in quantum computing, Hilbert spaces are where qubits live and they evolve. And every computation we perform happens inside this vast mathematical abstract world, and understanding its properties is key to unlocking the full power of quantum computing. Just one point I want to highlight, just have a bit of more detailed attention to these words. That is, whatever we perform happens inside this vast mathematical world. What do I mean by that? So your quantum state, why it's called a vector now, right now you will understand, because Hilbert space is also a vector space, it's also a part of the inner product space. So everything is very much related. It's just some kind of a completeness that you are applying onto your initial inner product space, where you believe that right now, if you do a certain manipulation, again, step will change, certain amplitude will change, certain phase will change, and it will reside somewhere else into the glass sphere or into that Hilbert space, mathematical abstract space. So it ultimately will reside into the same space. That is the concept of Hilbert space. And it is as if now kind of a like that kind of a place where theoretically it is able to hold everything that is possible. Everything that you are able to encode, it should be able to process it, or it should be able to hold that one. That theoretical abstract space is called a Hilbert space. And for those who have asked like inner product and outer product, like inner product is where basically you have two vectors that you are multiplying in order to get a scalar vector, and outer product is basically where you are getting a certain form of matrix as your output. Okay, so here actually the concept of conjugate will take into like picture. So you can think it of with certain examples. So maybe if you can find any example, we can actually discuss it. Just try, okay, just try to think of a certain quantum states, as you already know, through the bracket notation. Just try to multiply it or try to find the inner product of it. If you can check certain scalar value is coming, then it's called an inner product space. And if some vector matrix is coming, you can call it a vector space or a kind of an outer product space. Now, for that, what I want you to do is just check what your constituents should be, like what your A and B should be in order to get a scalar at output, and what your constituents should be in order to get a matrix as your output, right? So then you can also understand the different concept of the conjugate thing coming into picture, where some of the complex elements will be there, if they will not be cancelled out, and all those things. Just try to put 2 examples for that. Okay. So now it is basically, we will start with a bit of the quantum computing, fully quantum computing part. So which will continue from the quantum space or the quantum like states, that concept. That what is a qubit and what is a bit. So till the time we have today, our aim will be, I don't know how much time is left, or maybe say 30 minutes or something. Yeah, around 30 minutes, 25 minutes. Our aim will be to look into some of the computing things, so that whatever we apply, we can actually see those things to happen in real world. So qubits is nothing but a quantum bits. A bit is nothing but a binary digit, or whatever we have is the classical one. So in a bit, we have a degree of freedom that can take only 2 possible values. But in case of a qubit, it can take any of those values, like 0, 1, even another combination of zeros and ones. So it's a very minimal quantum physical system. The Boolean observable of a qubit system is called a sharp observable, as it can only have the value zeros and ones. A qubit can have another observable which has an equal probability of 1 and 0. Individual probabilities summed will result to a unity. And in real applications, I guess we have certain thing of these things in detailed way in later classes or later like sessions for what qubit exhibit superposition. So only y 0 and 1. No, qubit exhibit superposition means qubits can exhibit. Do not like change the word can here. Just put more emphasis on can. It is able to. Like if you want it to behave like just like a pure state, it can also do that. It can also do that. So it's your choice. It's absolutely the choice of a like developer. If you want to make it as a pure state, that is, if you want to encode only 0 and only 1, not any superposed thing, then it will be doing it. If you have a certain like a mixed state concept, or if you want to encode or want to perform superposition, then you are able to do that. So that is the ability that quantum offers or qubit offers. Okay, but definitely if you want to encode only say quantum thing, you can do that. If you just refer yesterday's class, we initially started with a 1 qubit quantum system which has only one state. Right. Now, when measured, it will collapse to 0 or 1. It will happen if it is already in superposition. See, if I have a superposed state, then at the output, we can get either a 0 or a 1. If it is perfectly unbiased. Okay, if it is 50% of 0 and 50% of 1, I do not have any contextuality on how it was built, and I'm just measuring it, I can get either a 0 or a 1. It will collapse. But if I have exactly one quantum system or one state only I'm encoding, only 0, I'm not doing any Hadamard, I'm not doing anything else on that. It's just a pure state on that 3D ball. Then it will be, if I put an output or try to measure the output, only 0 will come. If I have 1, only 1 will come. But if I have a superposition of 0 and 1, and if I do not have any knowledge, or if it is absolutely unbiased, then I can see a quantum computer. Okay, just gone. Okay, let us just discuss the questions at the very end. But if I have a certain kind of a quantum system, a 1 qubit quantum system that is able to process 2 states, that is 0 and 1 simultaneously, then I have a provision to measure while I will be measuring either to get 0 or to get 1. That is only when we are doing it, or collapse can only happen when I have a red and a blue ball together, that way which I can visualize. If it is only a red ball that I can visualize, then of course at the end I will be getting only red. From where the concept of blue ball is coming into picture. Similarly, if I have just a blue ball, or like entirely the ball is blue colored, then at the output I will be only getting the blue ball. If I have a red ball and a blue ball, and I can see both the things, it is like spinning. I can see once it is red, now then it's blue, now it's red, then it's blue. Likewise, then when I will measure it, or I will just pause the ball, I can see only one color. That was the thing. That was the thing. In qubit, what are the observables? Okay, so observables here is nothing but basically the operators. When at the time you measure it, you will yield to a certain values, either 0 and 1. That is the concept. If you just recall, in our last class, we were discussing that observables help us during measurements. So it is any of the observables that will lead to any of the outcomes. Now, what outcome you want to have, accordingly you need to put your observables into the picture. Okay, now it is nothing but, unless classical, in quantum it is nothing but a certain operator that can give you a certain outcome with a certain probability. That is an observable that you have to take in mind. And multiple times if you do some measurement, it will give you a certain probability. Okay, we will do the maths. Don't worry. We will be like seeing everything. We'll having like 4 to 5 times each of the topics in a different quoted way. So that we have a better understanding, very detailed understanding. So right now, please just for now understand what is a bit. It's a binary digit which can have either a 0 or a 1. A quantum bit, it can have both zeros and 1 together, but it can also have a 0 or a 1. So basic definition. And okay, and in reality, electrons either up and down, spin up and spin down, can represent a qubit. A polarization of photon, either horizontal and vertical, that can represent a qubit, which we do for the quantum communication thing, the photon polarization. The spin of atomic nucleus, that is also another realization of qubit. Current in a superconducting loop, that can yes, that is what I am discussing right now. So how to create the quantum bits in a physical way. There are a lot of other ways, there are a lot of technologies, so we had a detailed session for that. Right now I'm not entering into that. That's a physical level of like implementation of these things. Okay, so these are a few ways you can do that. So presence and absence of a particle can represent a certain qubit configuration. Current in a superconducting loop, that can represent spin of a nucleus, that can represent whether it's a 0 and a 1, and some intermediate spin will represent the intermediate states. The polarization of photon, either it's a vertical or a horizontal, that can represent the basis or pure states, where maybe 45° plus 45° polarization will represent a plus or a superposed state, and minus 45, which is 135°, will represent another superposition. Okay, likewise, depending on the polarization angles, if we define our qubit, that is one of the way. So likewise, there are different physical machine descriptions for superconducting qubits, ion trap, nonlinear photonics, linear photonics, quantum dots, topological qubits. So these are all the ways you can actually have a hardware realization of the qubits. Ultimately, the end logic for everything is either an on and an off. That is a thing. Now, how you are encoding an on and off, depending on that, you will be having different hardware variations of. Just I want to put one thing. Most of the cases, what qubit configuration or the kind of a hardware configuration is used to create a qubit is known as a superconducting qubits, which are followed by most of the companies like IBM, D-Wave, Rigetti. All these companies are following the superconducting qubit architecture. Okay, only one company is there called IonQ, which is following ion trap architecture. There are some new companies are coming, or some startups are coming, which are working on the topological qubits. But it is very much right now in a very niche level, niche research level, because they are just waiting to get that much of a decoherence free or a error free architecture, which is most likely less coupled and highly cohesive form of like qubit arrangements and all those things. So they are working on that one. But these are most widely used, the superconducting qubits, which is like used by maybe 90% or 80% to 90% of the like companies which are building qubits. And ion trap is another very like well-known architecture on which they're working. Ion Q. Okay. Now, computation with qubits, how does the use of qubits affect computation? In classical, you can see a filled bubble is 1 and a like empty bubble is 0. And its states are either 0 or 1. So likewise, you can either have a 0 or you can have a 1. Quantum computation data unit, it can be a 1 and a 0 in a Kate vector notation. Just check the notations right now also and check whether you are understanding it perfectly or not. So an up arrow represented by, here it is represented by 1, but it's again your convention. If you want an up arrow, you can represent with a 0, and a down arrow you can represent with a 1. Okay, so this is your representation, but whatever representation you will follow, your algorithm, entire algorithm should be built by that particular logic. So phi is basically C1 times 0, Ket0 plus C2 times Ket1. It is a superposed state. Then you just check the three diagrams present at the bottom of the second column where quantum computation is given. It's basically phi 0 as down, phi equals to Ket1 as up, and 0 plus 1 whole divided by root over of 2 as up, somewhere in between 0 and a 1. It's an average of 0 and 1. Again, I'm telling you, if you want, you can have a alternate like notation as well. And maybe in most of the cases, we will be actually following the alternate notation. Maybe up arrow represents a 0, down arrow represents a 1. That is absolutely okay. But whatever computation you want to follow, it should follow using the same notation. That is your like criteria. That should be your criteria. And accordingly, you have to define how you're going to encode the other states as well. So once you say divide somewhere from 1 and 0 or 1 and say superposed 1, you should start with that 1, not the 0. Likewise, so your positions and all should, everything should be in respect to or with respect to the your earlier assumptions that you are taking. Right now, we are taking, say up as 1 and down as 0. Are there any specific number of valid states? No, because Hilbert space, it is theoretically able to hold all the states as valid states. So there is no invalid state here. Invalidity or validity comes with the factor that how many of them are really realizable. Are they really realizable at this point of time? Is it really possible that the way I predict, say 00011011, if I increase it to say 4 qubits, so I'll be having 16 states. So whether how is the distinguishability of those individual 16 states are they really that much of a precise, that much of a clear way as it was initially when I had only 4 states? Is that kind of a precision or differentiability exactly same? If we have like only 4 states versus I have 16 states versus I have 32 states, that is the validity that should come to your mind. Okay, that is the concept of validity. Everything is valid, but it's just about how much of it you really can distinguish. Maybe they are so finely again like attached. There are a lot of other factors affecting it. But if you in general ask me that what is the validity thing, I guess you are asking between the number of physical qubits and logical qubits or algorithmic qubits that can work. So generally that ratio is 1000. So one logical qubit to replicate one logical qubit correctly, absolutely correctly, you basically need 1000 number of physical qubits. That is the current ratio. As per I know, as the last like update. Computational basis and probabilistic state vector also has to be very different. Computational basis states are nothing but those things what I was discussing, like 1 0 and 0 1. So if you have any other like specific question, just let me know. That is only computational basis states. And also just to give you a like glimpse of what we are thinking of, we are also thinking right now we have a NISQ era or a noisy intermediate scale quantum era, where we are assuming that our qubits will be noisy, but we have to tweak our algorithms in a way that it actually does not get much affected with the noise. But also there is a parallel research work going on which believes that a fault tolerant quantum era will come. So our algorithm should be able to tolerate all the faults and it should be working very well, assuming the noises and the errors and the decoherence will be very less. And in that era, how it can work. So similarly, it will work. What is the state equation during entanglement? So I think that is very irrelevant with respect to what here we are discussing. But yeah, entanglement, as I have just told in the last three classes, you can think it of like I have just told you, if it is a 0, 0 plus 1, 1 whole by root 2 is an example of yeah, I understand. I understand. Please, everyone, be very patient. It's very difficult. I agree. I completely agree. That is why I have split it into two parts so that something we can at least understand very easily from what we have studied in the last class, and something should be totally new. So, in that way, I try to divide it. If you have any question, then tomorrow we can start. For initial 5 to 10 minutes. I can like put for you all to ask me several questions based on only based on the content that we had covered in the last three classes. So that is doable. Please let me know in the very beginning if you want to put 10 minutes for that or not. Post that I will start, but it's definitely thank you, Dilip. So it's definitely very difficult. So we will be discussing those things as well. And for the one who has asked entanglement, just remember, so like as of now I have told you that there can be two cases, either like one input and another input, they can be in the same correlation, or it can be a different one, or it can be different one. So maybe 0, 0 plus 1, 1, it can be one way of entanglement that you can visualize, and say 0, 1 plus 1, 0 is another way, where in this latter case 0, 1 plus 1, 0 you are believing on the anti-correlation, and 0, 0 plus 1, 1 is somewhere you are actually visualizing through the same correlation. So that can definitely happen, but it's very irrelevant with respect to like the qubit representation. It's completely different one. It's a different thing. Yesterday we talked about. Okay, now I know these things are getting too much for those who are understanding or listening to it for the very first time. So I will just, can we say that the state vector is combined state computational basis? Oh, your question is a bit like complicated one. Just try to put it in a simple form so that I can understand it, or maybe just put it for the last end of the session. So that is why what I will do it, I will basically be using very slow pace so that every one of you understand it, and try to make it as much as relatable as possible. So for a single qubit one, Hilbert space is with respect to 0, 1. Just put a thumbs up if you're understanding what I am like I'll be telling you. If you have doubt, just post it in question. So Hilbert space is right now 0 is a 1, 0 and 1 is a 0, 1. So the basis vectors is basically a basis is a set of quantum states, and that basis you are putting into a Hilbert space. Okay, a 2D Hilbert space basically H2. Now H2 tensor product 2, it is H2 tensor product H2 is basically when you have 2 to the power 2, that is a 4 steps. So it's 0, 0, 0, 1, 1, 0, 1, 1. So likewise, you right now have a basis of 4 quantum states with you, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay, that is a Hilbert space. Now, arbitrary space is phi is equals to C1 times K0 plus C2 times K1. How I have written C1, C2 is C1 is a constant, K0 was 1, 0. So just you multiply, then it will be C1, 0 in a column vector form, plus C2 times Ket1. Ket1 is nothing but 0 and 1. Now C2 times Ket1 means C2 times 0, which is 0, and C2 times Ket1, which is C2. So it's basically C1, 0 plus 0 C2. Add it up, what will happen? C1 and C2. That is what we have written in the RHS in here. Okay. Now, similarly, if for a 2-qubit system, it's for a single qubit, first column, second column is for 2-qubit. If you have it like C1 times 0, 0 plus C2, 0, 1 plus C3, 1, 0 plus C4, 1, 1, we'll be getting like C1, 0, 0, 0 plus 0, C2, 0, 0 plus 0, 0, C3, 0 plus 0, 0, 0, C4. Add up the all 4 column vectors, then we'll be getting C1, C2, C3, C4. And the last one is operator. So if U is an operator that is working on state psi, then we'll be getting, what was your initial state psi? It was a C1, C2. Just look at the second row. It was C1, C2. And initially for 2 qubits, it was C1, C2, C3, C4. Right now, you can have an essence of an operator which is nothing but an observable. So observable in quantum is nothing but a quantum operator. That is the same thing. And how it helps to measurement. Yesterday, someone of you asked the question that how observable and measurement are different because they both feel like the same thing. Measurement is the act of measuring it. Once I've applied a few observables onto our quantum states, which are nothing but operators. So measurement is not the measurement is basically at what exactly you are getting ultimately at the macro level. That is the measurement, because whenever you are measuring it, you are losing, or you are actually the some sort of like it is coming back to the classical state or something, and classical is in the macroscopic level. But operator or an observable is not something that we are observing. Observable is something that we are applying in order to perform our measurement in the macroscopic level. But observable is something that is happening. If you are able to observe it quantumly, you can see a certain sort of differences in output. So it is happening in the micro level or the nano level or the quantum level. So observable happens at the quantum level. Operators happen at the quantum level after a certain series of operators or observables being applied on. Once we apply certain measurement operator, it is another operator, but once we apply the measurement, it becomes a macro level output that we are getting. So for example, U is a unitary operator. Yesterday, I will, like tomorrow, I will start with the Hermitian unitary and all these things again. We will start. Okay, but I will at least start with that one. So if you want to have a recap on the try to go to the fundamental levels of matrices and determinants and just learn what is a symmetric, antisymmetric, what is a all those things, Hermitian, skew Hermitian, all those things. If you want, you can have a detailed look at like into it. And what is a unitary matrix? What is normalization? Orthogonal, orthonormal, all those things. So U is an operator which is, say, for example, U11, U12, U21, U22. Once it is applied on C1 and C2, so this is how you look like. Now, it is a simple multiplication. The multiplier product I have not written. It will be like U11 C1 plus U12 C2 on top, and on bottom it will be U21 C1 plus U22 C2. So the output will be the output. It's basically 2 cross 2, and C1, C2 is a 2 cross 1. So ultimately, you will be getting a 2 cross 1 output. That is a column vector. But on top, you will be getting U11 C1 plus U12 C2, and on bottom, you will be getting U21 C1 plus U22 C2. That is a 2 cross 1 matrix that you will be getting as the output. Exactly similarly, a 4 cross 1 matrix you will be getting at output once you apply the unitary operator on this thing. Arbitrary state is one of the states that correspond to the Hilbert space. So it's basically a subset superset relationship. It belongs to the Hilbert space. Okay. So if you check it, like say for example 0, 1, 0, 0 or 1, 1, 1, 1, all these states are one of the arbitrary states that you want to perform. Okay. Thank you. Yes. So it's 3:57. I think we have 3 more minutes, but we will be about to start the quantum gates. So it will not be good to start today, the quantum gates. Until this part, I will be sharing. So just also remember that tomorrow we will start with first I will start with the basic theory of the linear algebra that is left. Start again with a certain kind of that thing like a Hilbert space, 1 or 2 examples of that. Then mostly I'll be covering Hermitian and the like skew Hermitian unitary operator. What is ortho orthogonal property, orthonormal property. Post that, I will start the concept of the quantum gates. So qubits till qubits, and right now for quantum computing, we have knowledge of qubits and quantum states, its difference with the classical states, and a few more properties of quantum mathematics also we have covered, right? So tomorrow we will be covering these a few left out properties, mathematical properties of quantum physics, followed by the quantum gates, which obviously will work on the principles of all those quantum physics that we are learning, mathematics of quantum physics that we are learning on today, and maybe also we will be in tomorrow's first stuff we will be covering. Okay, I'm stopping it.
Yeah, ma'am. In case you would like to answer any queries, you can look at that, ma'am. Some of the doubts are there, but I think, yeah, if you want to just engage for 3-4 minutes, any queries that are there in the chat. Otherwise, we'll conclude for the day.
Yes. Anyone has any like major question you can ask. If it is relevant, I will answer. Can qubit exhibit, okay, Rohitash Kumar Banial, okay. But qubit exhibit superposition, so why only 0 and 1? No, 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 no. Qubits can exhibit in superposition. They can exhibit in form of 0 and 1, but definitely we can, if we want, we can encode only the pure states. Just refer to yesterday's class. We initially started with, say, alpha K0 only, where we do not put any quantum state or any mixed state concept. But only a pure state is also a quantum state. It is not necessarily that a mixed state will be a quantum state. A pure state also is a quantum state. Okay, Rohitash, I hope that is clear now. Okay, there are a few questions on the like how qubits are like built up. I'm just like pausing it for the physical descriptions when we will be discussing about how the qubits are built up on the superconducting and ion trap, all those things.
तो MNAT ये ट्रिपल AT का है क्या ये?
Okay, computational basis state and probabilistic state vector also. Is there any difference, ma'am? Probabilistic state and state vector. Exactly what you are asking. So computational basis states is basically the individual quantum states that we have, and probabilistic state means that state can come up with a certain probability with respect to some other states as well. That is why I am understanding. So say for example, I have 4 states. Say I have 4 states here, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. And computational basis state is all these 4 states individually. So 0, 0 means 1, 0, 0, 0. 0, 1 means 0, 1, 0, 0. 1, 1 means 1, 1, like 0, 0, 0, 1. All these individual states are computational basis states. And probabilistic state means maybe the associated probability with respect to all those states. If we want to put those things in the like through some probabilistic amplitude, if we write it down, then it behaves as a probabilistic state. So definitely probabilistic state will apply on the probability will apply on the computational basis states. Yes, yes. So you can think it of in this way. Say for example, it's 1, 0, 0, 0. So it's 100% 0, 0. It's a computational basis state. But if you have say 1, 1, 1, 1, you can think it of like a 25% of all the like states, individual states, 0, 0, 0, 1, 1, 0, 1, 1. So if you have only 1, 1, 1, 1, it's a probabilistic state. You can think it of in this way. Okay. What are the last? Let me just check. From last time, just starting. Books of quantum mechanics I will apply. I will tell you. Encoding of quantum simulation error is coming. Isn't a good platform like this platform not support quantum teal? See, the base platform that I have seen is again the Qiskit one. So that is a best place you can like think it of. There are a few free real quantum hardware where you can do your coding if you want to, in order to get some real essence of how the quantum hardware will work on. And the simulation error also you will be getting a different kind of an error there. So that you can do. Henna. Okay. Can we take 4 qubit values at time? 4 qubit values, by this I mean that you are asking a 4 qubit quantum register. Can we just use it? Yes, we can use it. We can create a 4 qubit quantum register. So it will be having 16 states, and like in all the 16 states, how you will be encoding your information into those states, again, that is up to you. But definitely you can take 4 qubits. Okay. And if there is any error coming, please check onto their latest documentation. That will be helpful for those who are trying to implement it. Because there are like these are the errors which we also like get a lot of times. So maybe they just keep on changing the libraries and all those things. So just check what is the current latest update for that. Okay, I want to just pause it.
The chat also is being shared. Enter कर दो. This एक बार कर दो, post कर दो. हाँ. This is a chat. Chat link is given. These people are discussing various doubts and various questions. You are able to help one another. So please try to look at this. What do you say? This chat group. You can copy the link and just join. It's open for anybody who was interested to join. It's formed by the members here itself. All the faculty, some of them have joined. And the equal number of it's open to all the academies, in fact. So all of you can join, and you can keep sharing, and lot of discussion is going on. Of course, if you are interested, you can bear with it, but you can keep it whenever you have leisure, you can read it actually. So there are lot of information and a lot of discussion, lot of questions are being raised, and a lot of questions are being answered. Yeah, we'll thank Dr. Ms. Nivedita Day for her lecture today, and Dr. Ashwath for joining us. So we will meet tomorrow at 2 o'clock. Dr. Maipal Jadeja will coordinate tomorrow and day after. I'll be back on Friday. I'll be there. I'll be joining, but I'll be in IIIT Kota. So I'll be visiting there. So I'll join from there. But Dr. Maipal will be there to handle any queries. So please contact Dr. Maipal. And of course, if there's anything, you contact your respective academies if there are any administrative issues. Hopefully, we are trying to resolve all the issues related to Canvas, and we'll try to conclude that. Thank you very much. Thank you for joining.
Thank you, everyone.